Dear students, in previous class we discussed about the sequence and its subsequences. So now let us we have already seen that if a sequence converges to a limit, then its subsequence also converges to the same limit. Means a sequence and its subsequence has same convergence point. So now let us consider a theorem. If x equals sequence xn be a sequence of real numbers, then the following conditions are equivalence. The first one is the sequence x does not converge it. The sequence x means x equals xn does not converges to x following r. That is the first one. Second condition is there exists an epsilon naught positive, epsilon naught greater than 0, such that for any k following n, there is a natural number k with a nk following n. Then nk greater than or equals k, nk greater than or equals k with a mod xnk, modulus of xnk minus x, it is greater than or equals epsilon naught, greater than or equals epsilon naught. And the third one is there exists an epsilon naught is positive. Third one is there exists an epsilon naught greater than 0 and a subsequence x and k, x dash equals sequence x and k of x such that mod x and k, modulus of x and k minus x greater than or equals epsilon naught for all n, nk following n or for all k following n. So we have to show that these three conditions are equivalent. How to prove the equivalency? First, 1 implies 2. 1 implies 2. What is 1? Sequence xn be the sequence of real numbers. Then the first one is x equals xn does not converge this. X equals xn does not converge this means for some, that means by the definition of convergency, for some epsilon naught is positive, it is impossible to find a natural number k such that it is impossible to find a natural number k such that for all n greater than or equals k, the term modulus of xn minus x less than epsilon, the inequality does not possible. So it is less than x epsilon. Means for all epsilon naught is positive, it is since sequence xn of real numbers does not converge to x, then it is impossible to find a term for all k following n and n greater than or equals k mod xn minus x strictly less than epsilon. That means this inequality does not hold. So we have for all k following n, that means for all k following n mod xn minus x less than epsilon is not possible, means modulus of xn minus x, modulus of xn minus x greater than or equals some epsilon. Modulus of xn minus x greater than or equals some epsilon naught. That means let there exists, let xn k be a subsequence of xn. Therefore, since mod xn minus x greater than or equals epsilon naught, therefore mod xn k minus x greater than or equals epsilon naught for all n greater than or equals k. So 1 implies 2 finished, or mod xn k means there exists some nk. Agree? So 1 implies 2 means when sequence xn does not converge to x, then its subsequence xn k does not converge to x. So 1 implies 2. Now what is 2 implies 3? 2 implies 3. 2 implies 3 means what is 2? For epsilon naught is positive, there is a natural number k with nk following n and nk greater than or equals k mod xn k minus x greater than epsilon. So the subsequence mod xn k minus x greater than or equals epsilon naught for all k fall in n. So let epsilon naught is positive. Let epsilon naught is positive, comma n1 fall in n. n1 is a natural number. Then according to second argument, modulus of xn1 minus x, modulus of xn1 minus x greater than or equals epsilon naught. Okay. Again, there exists n2 fall in n such that n2 fall in n such that n2 greater than n1, then with a modulus of xn2 minus x greater than or equals epsilon naught. Again, there exists n3 fall in n such that n3 greater than n2 with a modulus of xn3 minus x greater than or equals epsilon naught. So, proceeding in the same line, finally you will have x mod xnk minus x greater than or equals epsilon naught for all nk greater than or equals n. Sorry, for all nk fall in n. So, 2 implies 3 finished. Now, what is 3 implies 1? Next, 3 implies 1. How to prove this 3 implies 1? What is 3? For epsilon naught is positive, there exists a subsequence xnk of x. Let it be x dash with a mod xnk minus x greater than or equals epsilon naught for all k fall in n. Then we have to show that the sequence x equals xn of real numbers does not converge. If possible, it converges. What happens then? If possible, it converges, then by the subsequence, then the subsequence x dash would also converge if possible. If sequence xnk, so sequence xn of real numbers converges to x, then we can say that the subsequence x dash of this xn should converge to x. That means the subsequence xn x dash means xnk minus x strictly less than epsilon naught for all nk fall in n or nk greater than or equals some k fall in n. That's a contradiction to this hypothesis. Hence, that contradiction is due to our wrong assumption. Therefore, the sequence xn does not converge to x under this condition. Hence, 3 implies 1 is also finished. Okay. So, these are the 3 conditions. If sequence xn does not converge to x, then 1 implies 2 means the subsequence does not converge to x. If the subsequence does not converge to x, then the sequence xn does not converge. Okay. So, now let us consider the divergence criteria. So, for convergency, we said that sequence xn of real numbers is converges means modulus of xn minus x less than epsilon for all n greater than or equals some k fall in n. And we also say that when a sequence converges, then its subsequence converges to the same limit. So, for the divergence criterion, let x equals xn be the sequence of real numbers. Then, if x dash and x2 dash are any two subsequents of this x, then if limit x dash differs from limit x dash differs from limit x2 dash, means x dash and x2 dash have 2 different convergence points and also the x is unbounded. Then this is the criteria for divergence. A sequence x equals xn is divergence whenever it is unbounded, as well as 2 of its subsequents have different convergence points. X equals xn be a sequence of real numbers. It is divergence when let x dash and x2 dash are any 2 subsequents of this x, then x dash and x2 dash have distinct convergence points. That is, limit of x dash strictly differs from limit x2 dash. So this is the divergence criteria for a sequence. For example, you consider a sequence xn equals minus 1 power n. Minus 1 power n means it is minus 1, 1, minus 1, 1, minus 1, 1, etc. Okay. Let x dash equals minus 1, minus 1, minus 1, etc. That's a constant sequence, minus 1 sequence. x2 dash equals 1, 1, 1, etc. This is again a constant sequence. What is the limit point of x dash? It is converges to -1. The second sequence x2 dash converges to 1, means they have distinct convergence points. Therefore, the secant xn -1 all power n is diverges. Okay. Suppose consider another one. Sequence x equals sequence 1 by n. 1 by n means, sorry, not sequence 1 by n. Consider sequence x equals xn, it is 1, 1 by 2, 3, 1 by 4, 5, etc. Consider this sequence. So how to define here? Here the subsequence or x equals xn. Here x equals xn is defined as it equals n if n is odd. Okay, n if n is odd. 1 by n if n is even. Okay. 1, 3, 5, when n is odd, the resultant is n. When n is even, 1 by 2, 1 by 4, etc. means it is 1 by. So consider xn1 or x dash. X dash equals n, and here x2 dash equals 1 by n, means what? Then x dash converges, then x dash and x2 dash has, so it is unbounded sequence. Okay, you have x dash equals n, x2 dash equals 1 by n. We does not say about, we cannot be say about the convergence points, but consider the boundedness of this sequence. X equals xn, n if n is odd, 1 by n if n is even, then the sequence is an unbounded sequence. Therefore, secant x equals xn is a divergent sequence. Okay. So, this is the divergence criteria. Means, if the sequence is unbounded, when a sequence is unbounded, it is diverges, or any two subsequence of the given sequence has distinct convergence point, then the sequence is also diverges. Now we define another term, that is peak. Means, consider let x equals consider definition, let x equals xn be a sequence of real numbers. We say that the mth term of this sequence, mth term of the sequence means xm. The mth term of the sequence x, that is xm, is said to be peak. Xm is said to be peak, peak, if xm greater than or equals xn for all n greater than or equals m. Xm greater than or equals xn for all n greater than or equals. Okay, yes. Means, you consider a decreasing sequence. Suppose x1 greater than or equals x2, greater than or equals x3, greater than or equals etc. So, we have for all n greater than or equals m, xm greater than or equals xn, then xm is said to be p. So, in the light of that definition, here in an increasing sequence, consider this decreasing sequence, x1 greater than or equals x2 greater than or equals x3 greater than or equals etc. So consider this in a decreasing sequence, each term is a peak. Each term is peak. x1 greater than or equals x2, x2 greater than or equals x3. So each term is a peak. In a decreasing sequence, each term is peak. Now consider increasing sequence, y1 less than or equals, y2 less than or equals, y3 less than or equals etc. So that's an increasing sequence. In an increasing sequence, there is no peak. Okay. So peak means xm greater than or equals xn for all n greater than or equals m. So for a decreasing sequence, each term is a peak, but for an increasing sequence, there is no peak. No term is a peak. Enough. So now let us discuss an important theorem. The theorem is known as monotone subsequence theorem. Theorem is known as monotone subsequence theorem. What is monotone subsequence theorem? The theorem says that if x equals xn be the sequence of real numbers, then there is a subsequence of x that is monotone. That is monotone subsequence theorem. If sequence xn, x equals xn be a sequence of real numbers, then there exists a subsequence. There exists a subsequence that will be xnk of x which is monotone. Monotone means either it is increasing or it is decreasing. Enough. So, it's case first. Consider, we say that a sequence X has if an increasing sequence, it has no peak. For a decreasing sequence, each time is a peak. Xm greater than or equals Xn, for all n greater than or equals M, then there is a peak. Then consider, if a sequence has infinite numbers of peaks. If a sequence X, here X, given sequence is X, if X has infinitely many peaks. First case, X has infinitely many peaks. X has infinitely many peaks. That means, let xm1, xm2, etc. are the peaks of X. Then, for such that m1 less than m2 less than m3 less than etc. Then that implies xm1, since they are peaks, xm1 greater than or equals, xm2 greater than or equals, etc. Okay. Let x dash equals, xm1, xm2, xm3, etc. So what about this x dash? This is a subsequence of the given sequence xn, then that is xm1 greater than or equals, xm2 greater than or equals, xm3 greater than or equals, etc. means the subsequence xnk is monotonically decreasing. Monotonically decreasing means the subsequence is monotone. That's a decreasing sequence, hence the subsequence xnk of x is decreasing means it is monotone. So this is the first case. If the given sequence has infinitely many peaks, infinite number of peaks, then the subsequence is a decreasing sequence, means its subsequence is monotone. Enough. Case second, if the sequence has, if x has only finite peaks. Finite peaks. Finite peak means let x1 or yes, let xm1, xm2, etc. xm2, etc. xmr are the peaks of x of the given sequence x. Okay. Such that with m1 less than m2 less than m3 less than etc. less than mr. For m1 less than m2 less than m3 less than etc. less than mr, xm1, xm2, etc. xmr are the peaks of the given sequence. So put s1 equals put s1 equals mr plus 1. Put x1 equals mr plus 1. Then what is xs1? So xs1 is not a peak. Why? Because there is only finite peak, means xm1 greater than or equals xm2. So since xm1, xm2, etc. xm are the peaks, means xm1 greater than or equals, xm2 greater than or equals, etc. greater than or equals xmr. If s1 is mr plus 1, then xs1 means xmr plus 1 is not a peak. Okay. Then if s1 equals mr plus 1, then xs1 is not a peak. That means there exists some s2 greater than s1 such that xs1 less than xs2. Such that xs1 less than xs2. Clearly xs2 is not a peak. xs2 is not a peak means there exists some s3 greater than s2 such that xs2 less than xs3. Clearly xs3 is not a peak. So proceeding in the same line, we get a subsequence x dash equals xs1, xs2, etc. Means that subsequence such that xs1 less than xs2 less than xs3, xs1 less than xs2 less than xs3 less than etc. means it's an increasing sequence. So the subsequence is increasing means it is monotone. So if x is the sequence of real numbers, Then there is a subsequence of x which is monotone. Subsequence of x, that is monotone. That is monotone subsequence theorem. So the theorem depends upon the peaks. If the sequence has infinite number of peaks, then we get its subsequence is a decreasing sequence, and if it has only finite peaks, then the sequence has an increasing subsequence. If xm1, etc., xm2, etc., xmr, xm1, xm2, etc., xmr only finite peaks, then s1 equals mr plus 1. Clearly xs1 is not a peak. Since xs1 is not a peak, there exists s2 greater than s1 with xs1 less than xs2. Clearly xs2 is not a peak. Then there exists s3 greater than s2 such that xs2 less than xs3. xs3 is not a peak. Proceeding in the same line, then you have a increasing sequence xs1 less than xs2 less than xs3, etc. Thus this subsequence is an increasing sequence, hence x has a increasing subsequence. Agreed? Okay. So this is the monotone subsequence theorem. Thank you.